All right, one more example for class 19. Here is 5119 from the ninth edition of Boronaki. And we have a cold day, it's negative 10 degrees Celsius, and a heat pump is used to, it provides 20 kilowatts of heat to the house and maintains it at 20 degrees Celsius. And it has a coefficient of performance for a heat pump of 4, using the maximum power available, right? So it can't use any more maximum, that's it. Any more power, that's it. The next day, a storm brings the outside temperature to negative 15 degrees Celsius. Assuming that the coefficient of performance changes by the same percentage as a Carnot unit would, and that the house loses heat to the outside air, and that the house loses heat to the outside air. How cold is the house then? That last statement is weird there. And that the house loses heat to the outside. Well, it usually does. How cold is the house then? This is a weird, no, it's not that weird. I like the premise, but some of the execution here gets me a little bit head scratchy. Let's see. Let's look at it again. All right, so I drew a little house. I just like drawing a little house. Maybe is that it? I don't know. Anyway, here's our we're going to put we're delivering QH in here, and outside we have this heat exchanger and mechanism coming up here, and here's our QL. And of course, we have our W. So here you go. There's all, and they're all dotted, little dots. So we want to, we know that Q1 is 20 kilowatts, and we know that coefficient of performance of the heat pump 1 is 4. So on day 1. The temperature outside is negative 10 degrees Celsius. That's the T low right here. And we also, okay, so there's a trick in this as well. I should point this out. Okay. So the heat flow that we're about to find, no, we found the heat flow. There's the heat flow. Heat flow, maybe we should go, this is the heat H, right? The heat H. And is it the same using the maximum power available? Okay, I think this is 1. Yeah, that's my belief. This is 1. Yes. Keep going. We can, this is a trick, Q flow 1 right here, take and lump together this is just some coefficient, and then this is the area of the house, but we know that we have the delta T on day 1. All right, so we can solve for this combined thing. Right? So that's like a trick that you wouldn't have thought of probably, but sorry, I didn't write the problem. But if you think it around a little bit, you're like, okay, I can see that. So we have 20 kilowatts and divided it by, that's supposed to be delta T. I'm not being able to think at the same time. Delta T, so they're the inside temperature and the outside temperature, and they are 20 degrees on the inside and negative 10 degrees on the outside. So it's a minus minus, and so we just came up ourselves with a coefficient of 0.6667 kilowatts per degree Kelvin. All right, so these are coefficient and an area combined together. So this is like a heat transfer of how much insulation, right? You can think about, in heat transfer, you'll be doing this a lot more, right? Where we have some type of barrier to heat flow. And you'll be doing these types of problems, but not in this class all that much, I don't think. So the coefficient of heat, this heat pump is going to be QH over work, right? So that's the definition of it. So we can find out what its power is going to be, and that's going to be this divided by coefficient of performance heat pump. And so if that's 20 kilowatts and 4, then our power is 5 kilowatts max. So good. So far, so good. All right. So now it's they say that we want to have two different yeah, we're gonna have two different coefficient of heat pump for Carnot, two different Carnot heat pumps, right? So there's going to be day 1 and day 2. So the coefficient of performance of the heat pump Carnot 1. How many subscripts can you have? A lot, apparently. And you have one. No, excuse me. Trying to get this straight, Ted. TH1 over TH1 minus TL1. That's true, right? So a refrigerator, this would have been L on the top. For a heat pump, it's an H on the top. And what do we get? We get 273 plus 20. Okay. And the high is 20. And we have minus 10. So here's what the Carnot 9.767 was what our coefficient of performance would have been for a Carnot under the same conditions. It's 4 here, 9.767 is what it could have been, but we don't really care about that. What we're going to say is that the change in it, I'm thinking, we're going to use that. Okay, let's go to day 2. Day 2, the new low is negative 15 degrees Celsius. And what we want to do is maybe start with the Carnot area of performance. Yeah, let's go to COP heat pump Carnot 2. Now the only thing that we know is the low. We don't know the high. What we're actually, yeah, this is the high is what we want to find out on day 2 what the temperature is. H2 divided by TH2 minus TL2. All right. So TH2 over TH2 minus 15. Or you could just say plus 15. I mean, if we're going to be stupid about it. TH2. Wait. Got to be careful here. We might need to put the 273 in there because we're canceling out right there. So, I think that's what they did wrong in the solution manual. Yeah, I was looking at the solution manual and I didn't like their answer, and I think I know what they did wrong. This is where they went wrong. You needed this or I read it wrong, which is totally possible. So it's minus 273 minus 15, which I pathetically can't do in my head. Boom, 258. Well, now I can, now that I've actually done minus 258. So you just leave it like that. We don't need this other part. Okay, cool. So let's see if this works out. Because I won't even admit it. I don't want to admit it. No, okay. So there's one equation right there. Now we also know that it's 60%, the actual coefficient of performance, HP 2, that we didn't have to do, I don't need that comma in there, is going to be equal to COP HP 1, and but it's going to be by the ratio of the Carnot, right? So it's going to be, let's see, I think it's going to be 2 over 1, right? So it's going to be COP HP Carnot 2 over COP HP Carnot 1. Is that true? Yes. almost certain. And let me see, 1 second. And let's see, that's going to be 4, that guy, divided by this guy is on the bottom. We just had a 9.767. And then that's going to be COP, HP, Carnot 2, which we just got right here. All right. But we can also find, and here is where we're playing some games. We're going to be able to use the maximum power, and we're going to have what the heat, what the new heat rate is going to be. Now, something I should also mention, I didn't before, is that guy right there, this Q1 that we had, is going to be the same as the Q leak, right? So when you're pumping something into here, it's going to go out there. Why are you doing this to maintain the temperature? You're putting it into here because it's going to come out through the insulation and everything. And so that's this right here is going to be the Q leak. So the new Q leak, so Q, and I think this is an H is usually what we call that, right? Because that's going to be, it goes to the high end. 2 is going to be C times A times delta T on 2, day 2, right? So CA times T, let's see, what we're going to do, T, I'm sorry, T, inside versus outside. So T2, TH2, minus TL2, right? There's the outside temperature. In this case, we're going to do the same thing as we did up before, right here. So this is going to be the same value right in here, and yeah. So what we're basically going to go is say 0.6667 times TH2 minus 258, right? And lastly, go back to the original use of this and say COP HP2 is going to be Q dot H2 over this. And we know that we can only use this amount of power, so we might as well. So let's combine this, so we're going to plug this back into here. Let's combine this guy, which takes this right here, and puts in there. And let's take this guy and plug him into there. All right, so there's several things going on here, but this is the logical steps that we're using for this. Let's see if I can express this correctly. I have this guy. I'll start with this guy. I go 4 over 9.767. And instead of writing this, I'm going to write this. TH2 over TH2 minus 258. All right, so that's that. It's going to be equal to this Q right here, which is this 0.6667 times TH2 minus 258 divided by, and then this is what we got up above. It's 5 kilowatts was the maximum that we could do. And we can solve for TH2. And I haven't done it, but when I did it before, I wasn't using degrees Kelvin, and I don't think the book was either. And I was not getting it to solve. But if you get it to solve, there's a good chance that when you're going to get the answer in Kelvin, I think this is the guy that messes it up. That you had, if you didn't put this, because if this needs to be in Kelvin, which you do by making that, and this needs to be in Kelvin, so that this is in Kelvin, so the answer that you get should be in Kelvin. And I should pause this whole thing and turn it and see what happens with these values when I'm done. But I'm going to take it on faith that they got the right answer because I'm tired. You will find that you get 14.7 degrees Celsius. Now remember, this is positive, but that's the highest that you're going to be able to get this thing working, because you just maxed it out at your negative 10 degrees Celsius outside. Now when it's negative 15 degrees Celsius, the highest you'll be able to get the inside temperature is a positive 14.7 degrees Celsius. I misread that at one point. I'm like, how does it colder inside than outside? But the outside is negative 15. This is a positive 14.7. But it's a very practical type of thing as a what if type of situation, right? So if you have like a bunch of unknowns, but you still need to make an estimate, here's some assumptions that you could make and come up with some type of answer. So there is the end of that example. And I challenge you, if you're one of my students, just to work through that, and maybe I will while I'm not busy on my free time, and whatever that is, and see if the algebra works out. I bet it does. Have a good day.